All right. Before the break, we talked about kind of different ways of compensating a system or stabilizing an unstable system. So let's talk about it in general from a system perspective. But now let's start looking at it from a little bit more circuit viewpoint. So from a circuit viewpoint, what we're trying to do when we're trying to start with a system that looks like a blue curve, I mean, and you don't have sufficient phase margin, you want to go to an orange one. And one way to do this is to reduce the bandwidth of, or basically make your dominant pole even more dominant, right? Reduce the frequency of your dominant pole even more in such a way that by the time you get to the unity frequency, you have sufficient phase, right? So this method of compensation it's used a lot in circuit design. So how do we do that? Let's say if you had an amplifier. Let's say you had an amplifier with a resistive source and a resistive load, R1 and R2, and then you're trying to apply some sort of a VN, and you want to kind of like reduce the bandwidth of this thing. If you had something like this, as simple as that, a common source, what are some of the simple ways of reducing its bandwidth? Well, one of the ways to do it is that, let's say, imagine you have this, like what we call C-pi, CGS, C-pi, right, in a transistor. So what can we do when we have actually a pole at the input, right? So we have here, in this simplified version, we have a time constant. It's an uncoupled time constant. If there are no other capacitors, well, it would be the only time constant. So it would be tau pi, right? And how can we increase this tau pi? What's the simplest way to increase this thing? Well, the simplest way is to add an extra capacitor, right? So then your time constant becomes C1 plus C pi. So if you're adding an extra capacitance, you intentionally are lowering the bandwidth of this thing, which is not the best way of doing it, and we will see later. Yes?
Why would you necessarily want to add an extra capacitor instead of adding more resistance?
Oh, okay, that's a good question. Adding more resistance, where? To R1, right?
Yeah, in series with R1.
You could do that. There are other considerations that usually stop you from doing that. For example, noise, which we haven't talked about. Because if you increase the R1, the voltage noise of that R1 would be significantly higher, and then that would reduce your noise figure or noise performance of your system, for example. Now, we'll see, actually, there's another way. If your capacitor, this was happening at the output, R2, it would do something interesting. So let's talk about that. That's probably even a more interesting question. So let's say this is C2. Let's talk about this now. This is a good question. So let's say we actually did, instead of through R1, let's say I have an output capacitor, C2. And if you wanted to do it through that, if that was the only dominant time constant. So in this case, tau 2 is R2C2, right? Now, if you have an R2C2 time constant at the output, the question is that well, one way to increase it is by increasing C2, right? But what happens if I try to increase it by increasing R2? Now, let's assume that I can get the biasing and everything right? So let's say you don't have any other reservations, if we did that. Well, obviously, the time constant will go down, right? But would this change the behavior of the circuit? So let's start from here. So let's say this would be, the way we've drawn it, is single frequency, right? So this is basically 1 over tau 2. That's, I don't know. Tau 2. 1 over tau 2, right? Negative 1. Well, if this is omega, this is multiplied, it would be 1 over tau 2. Okay, so we have something like that, right? So now if we increase R2, if we increase C2, what happens? If we increase C2, the time constant goes down. So what happens, instead of having something like this, you will get something like that. So this is increasing C2. Now what happens if we increase R2? Well, the time constant goes up by the same, but the gain, the low frequency gain, also goes up. So instead of that, this is what will happen. You will get a new time constant, 1 over tau 2 prime, which is the same as the one that you got when you increased the capacitance by the same factor. But is this doing what we are expecting it to do? Is it doing what we want it to do as far as, for example, if you had a second time constant here, a second pole that you wanted to hit? You can see that increasing the capacitor is actually doing that. It's lowering the unity gain frequency, but increasing the resistance is not. Because yes, the time constant is going up, or the frequency of the dominant pole is going down, but by the same, but the gain is going up exactly by the same amount. So the product, which is the gain bandwidth product, does not change, which is basically the unity gain frequency. So there is a fundamental difference between adding a capacitor and and changing the resistors. And this is more visible here. It was not as visible here. I mean, if you had a voltage divider here at the input, if you had an R pi, then you lose more gain there too, if you do that. So there's something else that happens. But this is something interesting to remember, that changing of the capacitor and changing of the resistor will have different impact in the unity gain frequency, and this is important. So now, what else can we do if you want to think about these things? Are there other kind of variations of this? So in general, if you have some sort of a load like this, right, you can always introduce a capacitor in parallel with it, like what we did, right? But now the question is that, is there another thing that we can do? Is there a variation? So let's say we are adding explicit capacitors like this. What if, so right now the network we are using from an AC perspective is this, right? This is R2, and well, C2 is here, and R2 is here, right? This is the network we are using. This is our load network. This is the one that our dependent current sources are driving to ground. But if the C2 is an explicit capacitor we've added, we can always do something else to it. You remember, we can always introduce a zero by introducing a parallel branch, a parallel series RC branch. In other words, a series RC branch, R and C in series, in parallel with whatever you have. So in other words, it means just basically taking this C and introducing the resistor R. So let's rename these a little bit. So let's call this CC and RC, right? If you're introducing this, then how would this change the transfer function compared to just having an R2? Well, let's find out. What we are trying to find out is the impedance of this network, right? So we are interested in Z of S of this network. And we have the methods to determine this. We can write KVL and KCL, or even better, we can write the time and transfer constants, right? So what is Z0? When there's only one element here, really, right? CC is 0. What is it? R2, right? Because if CC is 0, it's open circuit, it doesn't do anything. What is Z1, or whatever, ZC? When CC is infinity? Parallel combination, right? RC parallel R2. What do you get when you are, and then the other time, you have to calculate the time constant. So you have a tau C, 0 really, but tau C, which is what? Which is, we are calculating the impedance. So we are driving it with a current source. So the null source becomes an open circuit. So what do we get? ZC is, tau C, sorry. Tau C is RC plus R2 times CC. So what do you get from this? You get, and if you just plug this in, what you will see is that this is R1, R2 plus RC, multiplied by that gives you R2, RC. You subtract this, so you get Z of S, which is R2, times 1 plus RC CCS, divided by 1 plus RC plus R2 CCS. You basically have 1 plus tau ZS divided by 1 plus tau PS. So you have a pole and a 0. So this network introduces one pole and it's 0. But you already have 2 degrees of freedom, CC and RC, right? That you have introduced, this capacitor and this resistor. So you have 2 degrees of freedom, but there's a limitation. This cannot produce any kind of arbitrary pole 0 constellation, right? What it can do is produce, so there's one constraint, that one of them is greater than the other one. Look at the time constants, right, for the 0 and the pole. we can easily see that tau p is greater than tau z, right? Because it has this extra term, R2C2, R2CS, right? This is R2CS, right? So if that's true, then it means that the magnitude of p is smaller than the magnitude of z. Magnitude of z. Meaning that your pole is lower frequency than your zero. So if you were to use this to compensate an amplifier, how would you do that? So let's try to make something a little bit more specific. And see what it looks like. So let's say you got this system which you originally had an omega 1 and omega 2. And then you are starting here, you go there, and then you have obviously the phase. So you have two poles. And you're trying to make it so that you have a phase margin of, let's say, around 45 degrees or so. So now this new load, if I replace my load, where some resistor that's acting as a load, if I introduce this branch in parallel, right, I can take that load. At low frequency, I still have that load. But so it wouldn't, my low frequency gain and everything doesn't change. But I introduce this pair of poles and zeros. And I will have, and both of them are left half plane pole and left half plane zero. So I have the ability to put a pole zero pair. The only constraint is that my pole will happen before my zero. The pole is lower frequency than zero, right? So I can add a pair of pole and zeros to this plot. But I can pretty much put them wherever I want, more or less, right? Because I have 2 degrees of freedom, the RC and CC. If I didn't have any constraints on the component values, right? I can put them anywhere I want. The only thing is that my zero will be before my poles. My pole would be before my zero. And the other constraint is that for it to be really practical, these guys cannot be way off, right? But we will deal with that. So where would you put them to compensate this, to make it better, to stabilize? Right now, if you look at our phase margin, if this is negative 180 degrees, this phase margin, and this is to the unity, this is tiny phase margin. So let's say I want to have at least a phase margin of 45 degrees or something like that. So what would you do with this pair of poles and zeros? Where would you put it? So how about this? If I put the zero on top of this guy, and I put that pole, so this is P and Z, here, what would happen? Yes, I start dropping earlier, right? I start dropping earlier, right? And if I pick them to be the correct point at the correct point, the zero and pole pretty much cancel each other, at least the first order, kind of this way, and I will get something like that. So by adjusting the location of this pole and zero, we can actually place it at the point where you get sufficient phase. Basically, around that point, you have 45 degree-ish or more. By the way, if we do this, do we get more? So let's say I make this asymptote hit omega 2 exactly at that point, at 1 unit. So you have a unity gain for this thing at omega 2. Would we get more than 45 degrees of phase margin or less than 45 degrees of phase margin if these were the only two poles? What do you think? And why? If we did this, we are making this asymptote intercept the x-axis at exactly omega 2. Would we get more phase margin than 45 degrees or less? Let me show you let me give you a few visual aids. This is the way the thing actually looks like. This is 3 dB lower at this point. So your omega unity is really here, which means that you're getting more than 45 degrees, which is good because you design to start with 45 degrees, you get more, so you have like a little bit of margin to play with. But do you see that by introducing this branch, this RC branch, you can actually move And by placing it judiciously, we can actually try to create a situation where you can actually have sufficient phase margin. And if the proper phase response. So that's one way to do it. Now, in general, so you can say, okay, I want to have something more complex or more sophisticated. So you can actually make more complex networks that have a combinations of zeros and poles and things of that sort, and can put them there to try to balance them. At some point, it may become a little bit of a silly game. And the reason it can become a silly game is that if you keep doing that too much, what it does is that it would actually introduce, you're assuming that the component values and the transistor parameters are not changed. You're relying too much on those being exact, but we know that they're not exact because the temperature changes, the parameter changes, one transistor may not look like the same as the other one because the doping levels are different, things of that sort. So there is so much you can do with this thing. The next level up really is to add an extra capacitor here, right? You can do a C2. And when,
Behavior doesn't change for that?
sorry?
Phase behavior doesn't change when you add that network.
When you add that network, okay, so now that's a good question. What happens to the phase behavior? I didn't talk about that. That's a good question. So here, think about it. The phase, if these two, if the 0 and pole right are on top of each other, they are basically canceling each other's effect. But then your phase would move this way. But this phase is not doing anything down there. I mean, there may be a little bit of a residual phase left here, maybe a couple of degrees because of that. But this is not going to significantly change the behavior down there. But that's a good question. The phase behavior does change, but it changes where it doesn't matter as much. Yeah, good question. Any other questions? Okay, so you can actually make these networks and make them more complex, and people kind of like can go knock themselves out. But just sometimes it's just not useful beyond a certain point. So now let's look at actual op-amp circuits. Some of the op-amps that we've designed before and looked at before from other perspectives. Now let's look at it from a stabilization perspective, meaning that we want to see what happens to their frequency behavior, high frequency behavior and stability as we go forward. So let's start with our simplest op-amp, really, that we built, right? The simplest op-amp that we made or designed was this one, right? You had a differential pair. Give me MOS or BJT, doesn't really matter in this case. Let's use MOSFETs. And then you had a current mirror off the top. So you basically, it converts the differential input to single-ended input, to single-ended output, V out. Right? And then you can imagine that you will have some sort of a capacitive load that can be dominating, CL. Now, what is the gain of this amplifier? We did calculate this before, right? If you call this, like, I don't know, M1, M2, M3, and M4, what you have is that we saw that there are really two signal paths here, right? There was one, the way we calculated is that if this is VID over 2 and this is negative VID over 2, this current is GM VID over 2, which makes this current GM VID over 2, and this current becomes injected, it flips signs, becomes, because to get rid of that minus sign, GM VID over 2. So both of them are injecting current into this node. These are the kind of calculations we did before, a fair amount of them, right? And the output resistance, what is the resistance, total resistance on that node to ground? Right? We've done this before. This was, for example, RO4. Looking down here, you see from a differential perspective, RO2. So the total output resistance, capital R out, is RO2 parallel RO4. Right? These should be familiar calculations to you. Okay, so now you have these two, and what is the, so one of the, obviously one of the poles is dominated, so we can see a high impedance node, right? That's how you get your gain. The gain of this thing was, so the gain, AV differential, is GM2 or GM1, doesn't matter, RO2 parallel RO4, or in other words, GM2 or GM1, whatever, times R out, the parallel combination. You can, if you I want to make it look a little bit better. GM1 R out. Okay, so that's the gain of this thing. This is the differential low frequency gain of this thing. Right? Any question? Why did I switch GM1 and GM2? They're the same thing. If they're differential, they're balanced. If the stage is balanced, they're the same. It doesn't matter. You can write GM2. Okay. The high impedance node is here. You have some load capacitance. So that forms potentially a large time constant, right? So let's call it tau 1. Now, what else should I worry about? If you think about this, we have a system with two signal paths. We have talked about this before, right? What happens when you have two signal paths? That's a recipe for something. A zero, right? If both paths have separate dynamics. If that's the only capacitor we have, then the two paths do not have separate dynamics. That's not the case. But in practice, they will, because there is a capacitance on this node. Let's call it, I don't know, CA. Right? If there is that capacitor on that node, then there are two paths whose dynamics are not exactly the same. One of them is kind of like slower than the other one, if you think about it. Which one do you think is slower? This path is probably going to be slower. First of all, it's going through PMOS, PFET, they have smaller GM, they have larger capacitance, and it's just got more stuff there. This path looks more straightforward. So this is probably a slower path, this is the faster path. And we'll see what that does in a few minutes. But other than that, we also have two time constants here. Now, are these two time constants coupled or uncoupled? Does shortening or opening of one change the resistance seen by the other one? No, right? Because the resistance seen by this guy is RON parallel ROP, regardless of whether or not this is AC ground, right? And the resistance, if you have only two time constants, you know that the other one has to be uncoupled, right? You can't have one, right? But in this case, it's easy to see. If you short circuit or open circuit this guy, the resistance seen by this guy still is GM3 of this one, or RM3 of that, not RGM, RM1 over GM3, RM3 of that. So there are two uncoupled time constants, and there's a zero in this system. So let's talk about it. Let's write the poles. So P1, the dominant pole, if the load, usually your load capacitor is large, and this resistor is large, is basically given by 1 over R out times CL, right? That's your P1. That's your negative, that's your first time constant, the dominant time constant. Now you have a second pole. Sometimes this is called the mirror pole. Some people call it the mirror pole. It's fine. If you want to call it that, doesn't matter. What is that? It's basically 1 over RM3 CA. You can actually write it as negative GM3 over CA. And then if I ask you, what is the zero frequency? Where is the zero? What would you say? There's a zero, right? By the way, is the zero left half plane or right half plane? Well, there's a capacitor, shortening of which results in non-zero output, right? Which one is it? It's this guy. Because if you short circuit this guy, still the signal can go through here. Half of the signal goes through. But polarity doesn't change. You only lose half of it. So it means that it's at left half plane 0. And also, so we can actually calculate it, right? If you want to calculate what the right half plane is. So H0 is whatever, like A0, AV, right? And H1 is half of AV. Well, HA, whatever. Right? So you can clearly see, and the time constant associated with this this thing, right? So the numerator will look like H0 plus HA times tau A, right? S. So if you factor this thing out, you will get 1 plus tau A over 2S. So the time constant of the 0 is going to be half of that. In other words, it's going to be twice the pole frequency. It's going to be 2p2. Because its time constant is half. Right? The 0 time constant. So where is the pole? So you can see the pole 0 constellation looks like this. So there's a P1, right? If you want to kind of look at the sigma j omega axis. So there's a P1, there's a P2, and there is a Z, a factor of 2 behind that. If it's linear or whatever, it just looks like that. If it's logarithmic, it looks very close. Not too far, right? This is a linear plot, but so this is Z. So if on a linear plot, it has to be twice as far. So this is Z, really. So your Bode plot, if you think about it, if you're trying to use it in feedback configuration, your loop gain is going to be this times f, whatever the transfer function looks like. So what do you have? You have a P1 here, and then you have a P2, where your amplitude starts dropping, and then you have a Z, where the amplitude comes back up. And in terms of phase, if you look at it, this gives you 90 degrees. This starts giving you another 180, but it comes back up to 90 because of that 0. Okay? Does it make sense? All right. So now let's say if you wanted to make sure that this is stable, you wanted to guarantee stability on this thing, what do we do? Well, it's relatively straightforward, right? I mean, so in this case, we know what the trick is. The trick is to, if you wanted to, let's say, shoot for a phase margin of around 45 degrees. So you wanted to say, okay, if I make my unity gain crossover from this side, from the low frequency, around P2, then I will get that much phase, and I have the 0 to help me out too a little bit, so I get more, possibly. So I want this, well, not this. This to happen. So I want my P1 to be pushed out to here so that the omega unity due to P1 coincides with P2. What is omega unity due to P1? Right? Omega unity, right? Do you agree that it's just P1, original P1, times the gain? A DC gain, A0. Right? Or AV. We called it AV here. Let's call it AV. AV0. So if I had a first order system, if you only had a first order system, if I pick this P1 prime times AV to be omega U, that would be fine. But now I want it to be P2. I want my omega 1 to be P2. So this is what we're trying to calculate, right? So it means that P1 prime, so this is it. And how do we compensate this? How do we push P1 down? So let's think about this from a circuit perspective. How can you push P1 down? What controls P1? We talked about there are two parameters, R out and CL, right? But we did discuss this a few minutes ago, that you cannot just use RL. Because if you just increase RL, what happens is that instead of this going down, this goes up. So you need to increase CL. You need to actually increase your load capacitance in this case, which is not necessarily a bad thing. It means that to be stable, you have to have larger capacitors, so you can drive a more larger capacitor. But so okay, so what are we going to get? We're going to get 1 over R out CL prime, the new value of CL, or whatever it is, or CL, let's say, times AV. Now, AV is GM1 R out. So you want this to be at least P2. So you want it to be smaller than P2, smaller than or equal P2, which is what? P2, this is magnitude of P2, is going to be GM3 over CA. Right? But look at this, and something interesting happens. So R out actually does not enter this equation because of that gain bandwidth product that we talked about. So all that matters in this calculation is the transconductance of this stage, the load capacitance, the transconductance of these transistors, and the capacitance here. So you can rewrite this very simply as CL being greater than or equal CA times GM1 over GM3. So it says pick a load capacitor that's greater than this value. Whatever as long as your load capacitance for this kind of stage is greater than this, your stage is going to be guaranteed to be stable with sufficient phase margin. So not only it's stable, but also its time domain response. So for example, if you shoot for a time domain response, phase margin of 60 degrees, the time domain step response is also going to be pretty stable. It's not going to be ringing or doing some sort of an underdamped, showing an underdamped response. Okay, fine. Okay, so that's for like a basic single stage op amp of like with single transistors. So what happens if you, for example, had a cascoded stage, right? Let's draw a simplified cascode version and see now what happens in this. So we saw that if we wanted to get more gain from the one stage, one of the things we did was a cascode. And we really needed the cascode on one side. So I'm going to just show that one side of it. So you have a basic mirror, let's say, on this side. We are doing this not to have to worry about the other side. That's simple, but distracts from the main point. So you have something like this. Let's call them, I don't know, M1, M2, M3, M4. What did I use? M5, M6, M7. Okay? And then now you still, so this is your output. And then let's say you have some CL here. So this is V out. What is the gain? Again, gain AV or A0 is GM of these guys. So now we still know that's the same thing, right? It's the GM of this and GM of that would drive these two nodes. So this is going to be GM VID over 2. This is going to be GM VID over 2. And then the total resistance on this node is what we need to evaluate, right? What is the resistance on this node? What's R out? Well, it's this resistance looking down in parallel with this resistance looking up. What is the resistance looking down? It's really RO of this guy times 1 plus GM of this guy times RO of that one. But roughly, it's GM4 RO4 RO2. That's the dominant part of that. Right? And looking up, it's going to be GM of this guy, GM7 RO7 RO6. Essentially, it's the intrinsic gain of these cascode stages times the resistance RO of the transistor that's sitting down there. I mean, there's something like 1 plus something term. But this is the dominant part of it, if it's operating properly. So R out total, so R out is going to be the parallel combination of these two, right? It's GM4 RO4 RO2 parallel GM7 RO7 RO6. So that's R out, and then it's driven by GM, so AV is GM1 R out. Now, this is a larger gain this time because your R out is larger, not because your GM is larger, right? The GM is about the same, but you could get larger R out. So that's for that. So that's your low frequency gain. Then what are the other capacitors we have to take into account? So for example, do I need to worry about this capacitor separately? No, because this capacitor, if you look at it, is in parallel with CL. It can be absorbed into CL, right? Because this is ground, AC ground, right? Same thing with this capacitor, this one, right? So all of those can be absorbed into CL. You're one capacitor, really. So what else is left? Well, there's a capacitance here, this capacitance and that capacitance, a capacitance to ground. And then there's a capacitance here to ground. And then there's this capacitor that we talked about before. So let's call it CA, CB, CC. Right? So there are these like 4 capacitors, I mean, in the simplified model. And these time constants are essentially, well, they're not exactly uncoupled, but they're not very strongly coupled. The ones that are not coupled, they're coupled, you can see if you short circuit this one, right, you change the output resistance here. And if you short circuit this one, you change the output resistance. But since this output resistance is so large anyway, right, we are not going to just take that, we are assuming that they are far enough from each other that we treat them as if they were uncoupled, but although they are not uncoupled completely. So you still have now you have 4 time constants, right? This time constant and these 3. So obviously this is the dominant one, right? This is going to be a dominant time constant. This pole P1 is going to be still very similar to the other one. It's going to be 1 over R out CL. So that's there. Then which one would you say is the next largest time constant? So this is not exact anymore, right? I mean, just because of those coupling between the time constants. This is an approximation now. Which one of these 3 would you say shows you the largest time constant? Well, let me ask you this question. Between CA, CB, and CC, which one is the larger capacitor first? CC or CA? Because there are 2 transistors there, right? That's the CGS of 2 transistors up there. These are the capacitance of 1 transistor, right? Here, this guy and that guy. This is the CGS of that. So this is a larger capacitor. Now, the resistance seen by it is also GM of the PFET, 1 over the GM of PFET. So I would say, let's say this is P2, this is P3, and this is P4, roughly. They're not too far apart from each other, but it's just the P2 is going to be, again, these are very approximate, right? GM, 5 divided by CA, P3. These are becoming very approximate, by the way, right now. Is GM 7 over CB, and P4 are roughly, I don't know, negative GM 4 over CC. So these are approximately where these things are. And you're trying to compensate this. You're saying, okay, well, I want to make sure that this is stabilized. So what do we do? Well, you have 4 poles according to this simplified model. So you have one P1 here, and then you have a P2, P3, and P4 down here. So you go up here, you start dropping, and you drop more, and your phase goes down, and then asymptotically you can get negative 360 degrees. So how do we compensate this? Again, the trick is to push this out so much that if this is the unity gain frequency, so this is basically your unity gain frequency happens around here or before, where you have some phase. Now, if these guys are close to each other, the phase contribution of these subsequent ones is important. So you may not even be able to shoot for here. You may have to shoot for somewhere lower than that, because these are 3 poles, each introducing about a fair amount of phase that can extend back. But let's just, for the sake of argument, let's say we want to kind of push this back. So what do we need to do? We need to make sure that this crosses here. So this is your P1 prime, or the new P1. And again, that would set a constraint on CL, which you can write similarly. It's very similar to the other one. You can do that, define that constraint and force that to be the case. So you basically then you push it out. So yeah, that's fine. There is a little bit of a fly in the ointment in both of them, which is that 0 that's introduced because of this dual path, right? So you have that 0, right? And that 0 roughly sits here, approximately. I mean, it could be back and forth. So that 0 pretty much to first order cancels one of the effect of one of those poles, right? Which is an okay thing, because the left half plane pole. So it's not as bad as this, but it still allows it. So the process then beyond this becomes a little bit of an iterative process. You shoot for something firsthand, then you evaluate it, you assess it, and then you see where it is. And you see if, okay, I need more phase margin, less phase margin, things of that sort. But the key takeaway from this is that it is actually the first non-dominant pole, or the first group of non-dominant poles, that determine your unity gain frequency. So if you want to remember something from this discussion, is that. So if you're designing an open loop feedback that you intend to stabilize and compensate, you need to focus even more than your first dominant pole on your first non-dominant pole. Because one pole you can always handle, right? We saw that the first order system is almost always stable. Well, it is always for kind of all sorts of nonlinearity even, right? So your first pole is not really what matters. And you actually sometimes may intentionally make it even lower. It's the second pole that would affect you a lot. And that's something to keep in mind for this kind of systems. Okay, so that's for that's a one single stage op amp. But we did design these two stage op amps, right? So let's see. So let's go to back here, and let's talk about a two stage op amp and see how things would be behaving in that case and how the compensation can happen. So the most basic two-stage op amp that we designed, for example, in MOSFETs, looked like this. So you started off with a differential to single-ended converter. In this case, we're starting with a PFET drive stage and an N-type mirror. Which went to a second stage, which was a common source with an active load. And then you also have a current source produced here, PFET. You have a reference branch probably. Then you have some sort of a reference current, which we are not going to show in great details here. So this is your differential input, M1, M2, M3, M4. What did I call these things? It's M5, M6, and M7. Okay? And then you have an output, V out. So first questions first, what is the gain of this thing? What's the DC gain of this stage? Well, it's two gain stages, right? The first gain stage is this. We just analyzed this, right? 5 minutes ago. So this is RO2, and RO4. So this resistance is RO2 parallel RO4. We call it capital R1. And let's call this capital R2, which is basically RO6 parallel RO7. And then, of course, the gain of the first stage is GM of this guy, let's say GM1 times R1, this resistance here. And then the gain from here to the output is GM6 R2. So this is your DC gain. Right? We've done these things before, so I'm just like, this is review in that sense. Okay, so those are the gains. Now, if you think about it, you can actually draw an equivalent simplified model for this. Because this whole stage, right, is producing a voltage here that is GM, so it's like a current source driving with the GM1 VID, which drives this resistance R1 to produce this voltage that then is used by this transistor M6. So this is GM6 V1, let's call this V1, to drive the output resistance R2, produce V out. So this is the way it looks from an equivalent circuit for the differential input. Now, what you can see here is that, okay, so what are the capacitors of concern, right? So you have the capacitance on this node, which is coming from combination of the capacitance of these devices plus the input capacitance of this guy. It's CGS. Let's call this C1. There is the load capacitor, CL, right? And now the question is that how can we obviously know that in these situations we are trying to make our dominant pole smaller. We've already talked about this, right? You did see several examples where we were trying to push the dominant pole down, right? Like this one, to make sure that we... So how can we do that? How can we do that effectively? The challenge would be in many of these situations, especially if it's an integrated design, that the capacitance that you need for compensation may be too large. Meaning that it would, and you know on an IC, you pay for what? You don't pay for the number of components. You pay for the area of the components. And capacitors can be quite area hungry. So it can actually, you can make a chip that, well, like 3/4 of it is a capacitor, which is not a very efficient use of, you know, the chip area. It can be expensive. So is there a way to use a small capacitor and make it look very large? We've seen this in a situation where it was an undesirable effect. But is there a way to make that a desirable effect or use it? Do you remember what it was? Miller capacitance, Miller effect, right? So if you have a capacitance across a high stage inverting gain, right, it would appear like a very large capacitor at the input. So you already have a little bit of a capacitance because of the CGD of this thing. But if we explicitly add a large capacitor here, let's call it CC, then this capacitor will appear much larger at the input here. By what factor? By exactly 1 plus GM of this guy times R out, by 1 plus gain of this thing. So it would produce a very large capacitor on this node, which is a high impedance node or a low impedance node. It's a high impedance node, right? Because it's ROs and then input resistance of a MOSFET, which is pretty high at low frequencies, right? It's infinity theoretically. Okay, so you have this capacitor. So this is called the Miller compensation, actually. A lot of times this is called Miller compensation. So you introduce this capacitor, and the question is that what does the frequency response of this thing look like? So if you look at this model, you have this C1 that was sitting there. You're introducing this CC here, and then you have an extra capacitor CL, the load capacitor. So the question is, what is the transfer function of this thing? Now, this is something that we've actually looked at before. When we analyze the common emitter or common source, it's exactly the same arrangement. This looks like a common source, right? With R1 and R2 being there. So we saw that basically the time constants, there are 3 time constants. There's tau 1, 0, right? Which is what? How many poles and how many zeros, by the way, in this thing, before we just even write time constants? How many poles? 2, right? Because you have a capacitive loop. So you have 2 poles. And how many zeros? 1. Left half plane or right half plane? Does the shortening of that capacitor change the polarity of that gain? So the gain from here to there is inverting, right? So if I short circuit, it becomes non-inverting. So it's a right half plane 0. So, and the time constants are simply just basically R1, C1. Tau L 0 is going to be R2, CL. And now tau C 0 is basically, you know, R left plus R right plus GM R left, R right times CC, right? So it's R1 plus R2 plus GM R2, R1 times CC. And you can write the rest of the transfer function. We did this before, and then there's a tau 1C or tau C2. So basically what you end up with is something like this. You will end up with, in the denominator, so you have A0, the transfer function, the transfer function H of S. You have the A0 times, in the denominator what you have is simply 1 plus the sum of the 3 time constants, 0 value time constants, right, times S, plus, now then we had, if you remember, we defined this thing which we called it C delta squared, which was the sum of the 2-way products of the capacitors. And that was basically R1, R2 times C delta squared, S squared. And in the numerator, you get a 0, which basically is 1 minus, let's call it 1 minus S over Z1 or Z. And Z, we know that it's basically GM over this capacitor. So the pole, so if you look at this, and now if you look at these time constants, these 3 time constants, one of them is really dominating, right? Which one is the dominating time constant in this group? Yeah, I mean, so it's this part, right? It's this part that would come in and dominate everything, right? So if you write that, just that part, so you can say roughly, approximately, this is A0, you have the 0 in the numerator, and then you have this is 1 plus R1, R2, GM CC. It's really GM6. All of these GMs are GM6s. S plus, then you have R1, R2, C delta squared, S squared. So you can see that in case that you have a large amount of gain here, this is really dominated by the Miller capacitor, the Miller multiplied capacitor. So P1 is roughly really determined by this. So if you look at that, you can simply say P1 is approximately negative 1 over R1, R2, GM6 CC, right? And you can use it to push down the pole where you want it. Now P2, what is P2? Well, if you think about it, if this is dominated by P1, remember, this is basically 1 minus S over P1, 1 minus S over P2, which you can write as 1 minus 1 over P1 plus 1 over P2 S plus S squared over P1, P2. Which basically means that if P1 is much smaller, one of them is dominating, this is going to be just negative 1 over P1. And therefore, if this is your P1, you can calculate your P2 by dividing this by P1. Right? Because that's P1, P2. And then you do that, you get basically what you get here for P2. Let me just write it here. So this is now approximation because we're calculating it that way. It's GM6 CC divided by C1, the C delta squared, which is basically C1 CL plus C1 CC plus CL CC. Right? So these are the 2 things you get. No, actually, let me just write this down here below. I'm just going to copy it down here because I need to do some stuff with that. So, okay. And the 0, in case you're interested, is GM6 over CC. And it's positive. Right half plane. Okay, so you look at these 2, you see that this is your P1. Okay, this is your first pole. You have a dominant pole. So how do we choose that? Well, we need to look at what these things look like. So we can increase, as we increase CC, you can see that P1, what happens to P1? P1 goes down, right? You can clearly see that P1 becomes smaller and smaller as you increase CC, which is what you want it. You can proportionately reduce it. Now the cool question here is that what happens to P2? Because P2 seems to also depend on CC, right? What happens to it? Well, look at this. If CC is much greater than CL and C1, which one of these terms in the denominator matter? The terms that involve CC, right? The second and third term. So if those are the ones that matter for large CC, then you will get C1 CC plus CL CC, and then you have GM6 CC. So CC's cancel. So what you end up with is going to be GM6 divided by C1 plus CL, right? So that's for very large CC. Now, where was this before? So this is P1 as in, so P1, so let's call this P1 prime, right? Where was P2 if you didn't have any CC? If you didn't have any CC, do you agree that it would have been simply just 1 over RLCL? Right? Because this capacitance is not here. It's just basically the time constant of this resistor, this capacitor, and these resistors, right? But now, look, if you look at this ratio, you will see that as a result, what happens as you increase CC, so let's say this was your P1, and this was your P2. So this is P1, and this is P2. When you increase CC, something really important and interesting happens. P1 starts becoming smaller. So this is what we expected, right? CC going up. But P2 actually becomes larger. This is called pole splitting. And this is why this kind of frequency compensation is so popular and so common. Because what happens is that it not only brings P1 down, but it also pushes P2 out. So if you look at something like this, a plot like this, let's get rid of the rest of the stuff here and save the plot. So what happens here is that as you increase C1, your P1 is going down, but your P2, instead of staying where it was, it also moves up. Is this a good thing or a bad thing? It's a good thing, because it means that you don't need to push P1 that far down. You didn't need to push it down. If it's going up there, you don't need to push it all the way down. You need to push it only sufficiently so that by the time it gets here, you hit your P2. So it allows you to get a higher unity gain frequency product, unity gain bandwidth product, right? This pole splitting. And this is very critical, and it happens very frequently, and that's why you see this kind of state very, very often. Now, there's one more thing. So remember now, this is all good and nice, but we didn't talk about this right half plane zero. Right half plane zeros are nasty, right, from stability perspective. Because what they do, they take the amplitude, they push the amplitude up, so they make you go this way, so your unity gain will happen farther out, but while they push your phase down. They do all the wrong things, right? So you have a right half plane zero that we just completely ignored up until now. It can come and mess you up totally. But there is this really beautiful thing that can happen, which is that if you actually take a resistor and put some sort of an RC or RZ, whatever you want to call it, in series with this guy, it's very simple to show that your zero now, the zero frequency, becomes 1 over CC 1 over GM6 minus RZ, which you can easily see. If you set RZ to 0, it reduces to that guy, right? For 0 RZ, when RZ is not there, it just basically reduces to what we had before. But look at this. As I increase RZ, what happens to the 0? So this is a right half plane 0, right? It makes the denominator what as I increase the RZ? Smaller, which basically means that the frequency of the 0 is on this side, right? It makes 0 larger and larger, so it keeps going to higher frequencies, right? Now, if I set RZ to 1 over GM6, what would happen? The 0 just disappears, goes to infinity, right? So that sounds like a good thing. We can get rid of it that simply. But we can actually do even more. What if RZ is greater than GM6, or 1 over GM6, or RM6? It comes back from negative infinity, right? So, and now it's the left half plane 0. So if you keep increasing RZ, what can you do with that? In theory, at least, you can actually come and bring it back and put it on top of your P2, and then now you're limited by P3. The next pole over. And that would determine your omega. Practically, you may not be able to push it this far out. But even if you can push it somehow close to this system, to this constellation of poles, it would reduce your phase, and it will start canceling the effect of some of your poles. So you will see this also very commonly, that when this compensation is done, there is a resistor in series. Sometimes this resistor is implemented as a MOSFET. That's biased to some in the triode region. not in pinch off, in triode as a resistor, if you want to make it tiny. A lot of times actually it's just done as a resistor. And that compensation helps you a great deal with that. Okay, so that's for frequency stability and compensation. And these are just some examples of how that can be achieved. There are lots of different variations of this and different ways of doing this. Any questions? All right? Yes, question. Sorry? How did we get P2? So if you remember what I did, you agree with this, right? So what happens here is that you have this is 1 over P1 plus P2. If we assume that this is P1, I just divided this by that. So R1 and R2 canceled. So it's basically this divided by that. Right? It's a GM6CC divided by C delta squared. Because if we assume that this is 1 over P1 and this is 1 over P1 plus P2, this becomes basically P2 becomes negative this divided by that. That's how it's an approximation. Because we are ignoring this P2 in this first term. Let's assume that P1 is much greater than P2. Or much smaller than P2, sorry, magnitude. Yeah. Any other questions?